Welcome to Math TV with Professor V. This is part 3 of the final exam review for Calculus 2. In this video, we're going to go over solving differential equations, both separable and linear, and then doing calculus in polar and parametric coordinates and conic sections. All right. So first type of differential equation that we're going to go over is a separable differential equation. It's first order, meaning first derivative is the highest order derivative in the equation. And it has to be set up so that the expression for dy dx can be factored as a function of x times a function of y. That's why we call it separable. You can separate a function of x from a function of y. And in order to solve it, all you do is you get dy on the same side with all the y's. You separate little dx, hence it's also separable because you're separating the differentials. You move dx over with all the x's, integrate both sides, try to solve for y. So let's do a couple examples. Solve the differential equation dy over dx, dy dx is e to the 5x minus 5y. And this is all in the exponent right here, okay? So first, let's see, how is this even separable? I need a function of x times a function of y. So you got to remember your laws of exponents. I can rewrite this as e to the 5x over e to the 5y, right? A to the m over a to the n is a to the m minus n. That's usually how you learn your laws of exponents. So I started with the right-hand side like this and broke it up into division. Ooh. Okay, now it's separable. Can you see it? Yes, we can see it, Professor V. Oh, good. So we're going to have e to the 5y dy equals e to the 5x dx. And then now's the fun part. We're just going to integrate both sides. Antiderivative of e to the 5y. Good. 1/5 e to the 5y. Don't put plus c on both sides. You only need it on one side. Equals, this will be 1/5 e to the 5x plus c. Now, last step is to try to solve for y if possible. It's not always possible, but in this case it is. So what I'm going to do first is get rid of the 1/5. So I'm going to multiply the entire equation through by 5. So then I have e to the 5y equals e to the 5x plus 5c. Okay, keep track of your constants. Now I'm going to take the natural log of both sides and then do so carefully on the right-hand side. So I have here 5y equals ln of e to the 5x. Oh, that's coming up. Plus 5c. All right, and then last step, we can solve for y if I just divide by 5. So I'm going to say y equals 1/5 ln, and then this is going to be e to the 5x plus, I'll call this k, just to clean things up, where k equals 5c. All right, and then let's box it. That's it. Not too bad, right? Okay, now moving on, let's look at another example. We have dy dx equals 3x squared cosine squared y. So this one, hopefully you can already tell it's separated. Here's my function of x. Here's my function of y. Let's separate. So I'm going to have, your differential cannot be in the denominator. So you're going to have dy over cosine squared y equals 3x squared dx. Before I integrate, I'm thinking ahead, people. Cosine squared y in the denominator, I can write that as secant squared y, and whew, that's easy to integrate. See, equals 3x squared dx. Okay, now let's integrate both sides. So antiderivative of secant squared y? Tangent y, very good. Antiderivative of 3x squared is just x cubed plus c. And then to get y by itself, we can just apply tan inverse to both sides. So y equals tan inverse of x cubed plus c, and then I would just leave it like that. okay? Don't invent some fake distributive property that doesn't exist. Don't be doing this kind of nonsense. The math police are going to come and lock you up. Okay, good. Separable, I think, are pretty easy and fun. Now, next kind of differential equation that you're going to need to know in Calc 2, wait until you take differential equations, is a first order linear differential equation. So it has to have the following form. You have dy dx plus p of x times y equals q of x. So p and q are just functions of x. They can be whatever. You just have to make sure you have only y to the first, okay? That's what makes it linear. And it's first order because also you only have a first derivative. You don't have like a second derivative in the equation. That would make it a higher order. All right, so to solve, you got to write it in standard form first. Then the little trick to solving these is you find the integrating factor I of x. I of x equals e raised to the antiderivative of p of x dx. You don't need to worry about the plus c when you find the integrating factor. You just get it, and then you multiply both sides of the equation by the integrating factor. And then the left side is I times y prime, or you could think of it as like d dx of I times y, or d, whatever variable you're using, theta, y, whatever. And then integrate both sides, solve for y, okay? All right, I think these are quite fun to do, actually. So here we go. We have cosine of x dy dx plus y sine x equals sine x cosine x. So first thing, we have to put it in standard form. So how do I know it's not in standard form? Dy dx is not isolated. Look, look, look. See how it's supposed to be all by itself? Okay. And then make sure the y is on that same side too. So here we go. I'm going to divide everybody by cosine x. So we have dy dx plus y times sine x over cosine x is tan x equals just sine x now, right? Because I divided by cosine x and it canceled out. All right, very good. So from here, let's go ahead, figure out the integrating factor. So I equals e to the integral of p of x dx. What's p of x? Whatever's multiplied by y. And if this is a minus sign, you need to include that. Oh boy. So there's no minus sign, I don't have to stress, but let's find the integrating factor. E to the antiderivative of tan x dx. This one you should memorize. If not, you could u sub it, but it's e to the ln absolute value of secant x, which is just absolute value of secant x. Okay. So from here, now let's go back to this differential equation, and we're going to multiply everything through by absolute value of secant x. All right. And for just to make things easier, we're going to assume that secant of x is positive, which means I'm assuming cosine of x is positive. So we're just going to say, let's just say x is between negative pi over 2 and pi over 2. So we don't have to worry about keeping the absolute value, just to make life easy. Okay, so then now here we have dy dx times integrating factor plus y times tan x secant x. Everybody gets multiplied by the integrating factor, okay? Times sine x times secant x. Now, the left-hand side, as long as you did everything properly, will always be the derivative with respect to, in this case, x, the independent variable, of I times y. So secant x times y. Let's check. Is that true? So we would have to do the product rule. Derivative of secant x is secant x tan x. Oh, there it is. Leave y alone. Plus, and then if you left secant x alone and then you multiplied by derivative of y, there you go. All right. So after you multiply by the integrating factor, the left-hand side should be the derivative of the integrating factor times y, the dependent variable. Good. It is. We checked. Woohoo. So we're going to integrate both sides now with respect to x. You don't do anything on the left because pretty much this integral, and this is already a derivative, undo each other. So you just have integrating factor times y. And then we have to integrate sine x over secant x, or sine x times secant x, which is sine x over cosine x, which is tangent x. So then we have secant x times y equals ln absolute value secant x plus c. And then let's get y by itself. So let's divide everybody by secant x, which is the same as multiplying by cosine x. Yes, very good. So then we're going to have here y equals cosine x ln absolute value secant x plus c cosine x. And I did say early on we're going to assume x is in quadrants 1 and 4. So then we know this is not going to be negative. So I can just put parentheses. If you leave it absolute value, that's fine too. Okay. Good. Did you enjoy that linear differential equation? They're some of my favorite. I don't know why. I just love them. Okay. Yeah. Can you expect one on your final? Probably, if you're in my class. I don't know about your teachers though, what they're going to put. Okay. Here's a good one. Solve the initial value problem. So what does it mean? Why is it calling it an initial value problem? Well, it's a differential equation. You have to solve this first order. It's linear differential equation. And then they gave us an initial condition. That's what makes it an initial value problem, so that we can solve for c. So when they tell us y of pi is 0, then that's just an indication that at the very end, I'm going to find c and then get my answer that way. Okay? Good. So let's put it in standard form first. I have to isolate dy d theta. So I'm going to divide everybody by theta squared. So let's see, dy d theta minus 3 theta divided by theta squared is minus 3 over theta now, right? Times y equals theta cubed secant theta tan theta. And they told me theta is positive. Okay. So let's find the integrating factor. I of theta is e to the integral p of theta d theta. Watch out, you guys. You have to include that negative. Otherwise, things will quickly derail. So antiderivative of negative 3 over theta d theta, that would be e raised to the negative 3 ln absolute value of theta. And then that's e to the ln absolute value theta to the negative third. So this is absolute value of theta to the negative third. But these kind people told me theta is positive. So this is just theta to the negative third. Woo! Okay, what do? I multiply everybody in the equation by theta to the negative third. Let's do it. So we have dy d theta times theta to the negative third minus, that's 3 theta to the negative first times theta to the negative third, so 3 theta to the negative fourth, y equals, and then do you see these will just cancel each other out? So then I have secant theta tan theta now on the right hand side. Okay, let's check. Is this indeed the derivative, this time with respect to theta, of the integrating factor, theta to the negative third times y? Check. Don't be lazy and assume it always works out, because I've caught, some silly errors many times that have saved me. So just take the 10 seconds to check. Say I leave this alone. Derivative of y dy d theta. Good. We're doing product rule. Plus derivative of theta to the negative third. Yep, that's negative 3 theta to the negative fourth, and then leave this guy alone. Perfect. Everything checks out. Now you can continue with the clean conscience, How wonderful. So d theta, integrate. Okay. So now we have theta to the negative third y equals, what's the antiderivative of secant theta tan theta? It is secant theta. Don't forget plus c, okay? Now it's kind of up to you at this point. Do you want to solve for C now or after you get Y by itself? It doesn't matter. Okay, sometimes it's easier to find it at this step, or sometimes, if you forget though and you do it at the very end, whatever. So how do I find C? Well, they told me Y of pi equals 0. So I'm going to plug in pi for theta and 0 for Y. So pi for theta, so this is 1 over pi cubed, plugging in 0 for Y equals secant pi plus C. I just have to 0 on the left-hand side. Secant of pi is -1. So that means C is +1. Okay. And then now I know C is 1, so I'm going to sub that back there. Let's do it. So 1 over theta cubed Y equals secant theta plus 1. And then the last thing to do is multiply everybody by theta cubed. So Y of theta is theta cubed secant theta plus theta cubed. That's it. That one's beautiful. Woo. Good. Very good. Okay. I think we're good with most differential equations. I did want to show how to do a Bernoulli because I was promising my class I would. And I keep my word. So here we go. Now, for Bernoulli, it's a little different because it looks like it's first order linear, but something is ruining it. This y squared, why are you there? So let's start identifying what we know from our typical linear differential equation, and then I'll tell you the little trick. So we still have the same setup of like p of x, that's -1, and then q of x on the right-hand side is -x. And then since we have y squared, we have y to like some power. That's what makes it Bernoulli. We say n is equal to 2, the exponent, okay? So what we're going to do is figure out, we're going to make a u substitution. And u is equal to y to the 1 minus n. So this is 1 minus 2. Y to the -1st power. What is the point of doing this? Do a u sub the way you do with integration, kind of, okay? And then you'll see it's going to turn into a nice linear differential equation. So let's differentiate both sides with respect to x. Du dx equals, derivative here would be -1 over y squared times dy dx. Okay, hang tight. So we take the original differential equation. I'm not crazy about writing this as y prime, so I'm going to rewrite it as dy dx minus y equals -xy squared. And I'm going to multiply it now by -1 over y squared. Okay. And then look what happens here. So this becomes -1 over y squared dy dx plus, this is distributing. Now I'm going to have 1 over y equals positive x. Why is that good? Well, remember, -1 over y squared dy dx is du dx. So I'm going to replace that with du dx. Ooh, what an ugly x. Plus, oh, what's 1 over y? Same as y to the -1st. That's u. Equals x. Okay, now pretend this was what they gave us originally. This is a linear differential equation. Now it's linear. Okay, so let's go ahead and solve. Let's get the integrating factor. There's just a 1 right there. So integrating factor is going to be e to the integral 1 dx. So it's just e to the x. Now I'm going to multiply everybody here by e to the x. So e to the x du dx plus e to the xu equals e to the x times x. Let's check. This better be the derivative with respect to x of the integrating factor times, not y. In this case, we're working with u, right? Let's check. Check. So derivative of e to the x is e to the x. Leave u alone. Now leave this guy alone. Derivative of u. Perfect. Okay, then we're going to integrate both sides. Boom, ba-doom. Left-hand side is done. It's just e to the x times u. And then now this is a good review. How do you integrate x times e to the x? By parts. Okay, normally you pick u and v, right? But I already used up u. So I'll just say u bar dv bar. Excuse me. Normally you pick u and dv. Okay, so u bar is going to be x. dv bar is going to be e to the x dx. So v bar e to the x du bar dx. So this integral is going to be u bar v bar x e to the x minus integral du bar v bar, so e to the x dx. Good, we're almost there. Oh, I think I will need an extra wee bit of space. Nothing serious, guys, nothing serious. Oh, okay. So this is e to the x times u plus x e to the x minus e to the x plus c. Okay, now let's get u by itself. So divide everybody by e to the x. So then we have u. This should be an equal sign. What happened? I'm losing it. Okay, I'm going to pull it together right now. U equals x minus 1 plus c over x. I'll just write it as c e to the negative x. We're not done, because remember, we made a change of variables, and we let u equal 1 over y. So now we got to go back, replace it. So that means 1 over y equals x minus 1 plus c e to the negative x. And then to solve for y, I can just take the reciprocal of both sides, right? Like this is over 1. So then flip both sides. Y equals 1 over x minus 1 plus c e to the negative x. And you don't want to leave your final answer this way, because technically it's an improper fraction. Since c e to the negative x is c over e to the x, right? That's a no-no. So we're going to multiply everybody by e to the x. Okay. And then now I can finish everything off beautifully. All right, y of x equals e to the x over, let's put the c first, plus e to the x times x minus 1. Okay, there you go. If you have to take differential equations, you'll learn a lot more like various techniques and various different kinds of differential equations, and you'll have to figure out, you know, when to apply which solution technique. Similar to like how you integrate, and you just have a bunch of different kinds of integrals and you have to pick how to tackle each one. The course is very similar in that way. Okay, how we doing? That's it for differential equations. Now we're going to move on to parametric and polar coordinates and doing calculus with them. So parametric equations and a parameter interval for the motion of a particle in the xy plane are given. Identify the particle's path by finding a Cartesian equation for it. So Cartesian, same as like rectangular, just xy, okay? And then graph the Cartesian equation, include the portion of the graph traced by the particle and the direction of motion. All right, very good. So, you know, right off the bat, I see since x and y are given as functions of sines and cosines, I'm going to utilize Pythagorean identity to eliminate the parameter. Specifically, the fact that sine squared theta plus cosine squared theta equals 1. So since x equals 2 sine t, that means x over 2 is sine t. This is like a common trick you're going to do. And then since y equals 5 cosine t, that means y over 5 is cosine t. And then if I just square both these guys and add it together, then I know they have to equal 1, right? Good. And this is the equation of an ellipse. So we can draw it out already. It's centered at the origin. In the x direction, we're going to go 2 units. In the y direction, we'll go 5 units. And it should look something like this. Let me see. You know, can I get it to cooperate, or should I just draw it by hand? Let's just try drawing it by hand, because I feel like the auto draw doesn't always allow me to move it around. This is a deformed looking ellipse. My apologies. Okay. Now from here, they want us to indicate the direction of motion. I knew it was the entire ellipse. Sorry, I didn't mention, because t goes from 0 to 2 pi. So it'll trace out the whole thing all the way around. But to figure out the direction of motion, let's plug in a couple values of t to see where we start and where we finish, okay? So I'm going to plug in t equals 0. The x coordinate would be 2 times sine of 0, so that's just 0. 5 times cosine of 0 would be 5 times 1. So we start at 0, 5. We start right here when t is 0. Now don't plug in t equals pi or t equals 2 pi. 2 pi is just going to get you all the way back around. If you plug in t equals pi, I already know it's going to take me here, but I don't know, did it go this away or did it go that away? So plug in something, you know, not quite halfway. How about pi over 2? If I plug in t equals pi over 2, x is going to be 2 and y is going to be 0. So that's right here. That's t equals pi over 2. So it's going this way, and then it'll keep going and going and going. You can plug in more points if you need. I don't need. I feel good about it. So when it says here, indicate the portion of the graph traced by the particle, we did it. And the direction of motion, we did it. We put these little arrows. If you want to write in words, it's going clockwise, you can. Normal standard direction of motion is counterclockwise, right? That happens when x is cosine theta and y is sine theta. But since these guys are switched, then it goes the other way. Fun fact for the day. Okay, that's enough of that. So you'll probably have to do other exercises where you're eliminating the parameter, indicating the direction of motion, yada yada. Now let's talk about finding derivatives in parametric. So in this particular problem, they want us to find the second derivative with respect to x at the given point. So remember, dy dx is dy dt over dx dt. That formula should make complete sense. It looks like the dt's are canceling out. That is not what's going on, but if it helps you remember it, cool. Second derivative formula, a little trickier, okay? You take the derivative with respect to t of this first derivative, okay, of dy dx. So you take another derivative with respect to t, and then you divide by dx dt. Remember that it's not just second derivative of this over second derivative of this. No, no, no. Okay, so here we go. X is cosecant t. So let's take the derivative, dx dt is going to be negative cosecant t cotangent t. Yes? Yes. Okay. And then y is 2 cotangent t. So dy dt is negative 2 cosecant squared t. Okay. So let's figure out dy dx. It's just dy dt over dx dt. So negative 2 cosecant squared t over negative cosecant t cotangent t. Okay, good. So the negatives cancel. This cosecant cancels with 1 in the numerator. So now I have 2 cosecant t over cotangent t. And I would say always try to clean it up as much as possible, because you know we're going to need another derivative, right? So if I can get this clean enough that I don't have to do a quotient rule, whew, I'm in good shape. So let's see, 2 cosecant t, that's 2 over sine t over cotangent t, that's cosine t over sine t. Oh, see how lucky we are? This cancels. Boom, boom. And then I just have 2 over cosine t. But you guys, that's just 2 secant t. Hooray. That's perfect. It's going to be so much easier now to differentiate, yes? Good. Okay, so here we go. So second derivative, you take the derivative with respect to t of 2 secant t, and then this gets divided by dx dt. Where are you? I'm here. Okay, thank you. So negative cosecant t cotangent t. Okay, so derivative of 2 secant t, do you remember what it is? 2 secant t tan t over negative cosecant t cotangent t. Now, at this point, if you want, you can already plug in t equals pi over 3 and evaluate it, because that's all they're interested in, is what is the value of the second derivative at that point. I'm just going to clean it up more just so we have more practice. I feel like a little extra trig never hurt anybody. So, 2 secant t, that's 2 over cosine t, times tangent t, that's sine t over cosine t. And then I'm already going to start flipping stuff. So like cosecant t in the denominator means I have sine t in the numerator, right? And then let's just bring that negative in the front. So I have another sine t over 1. And then cotangent t in the denominator means you really have another tangent t. So I have another sine t over cosine t. Did anything cancel? No. Oh, that's depressing. Okay, so the second derivative is going to be negative 2 sine cubed t over cosine cubed t. Yeah, sure is. So that's negative 2 tangent cubed t. And then now let's evaluate it at, oh, I gave myself so much room. T equals pi over 3. So that's negative 2 times, what's tangent at pi over 3? I still think of sines and cosines. I go, ooh, at pi over 3, sine is rad 3 over 2, cosine is a half. The 2's cancel, so it's just rad 3 over 1. If you cube rad 3, it's 3 rad 3. So this is negative 2 times 3 rad 3, so negative 6 rad 3. And that's all they wanted. They wanted to know what is the value of the second derivative when t is pi over 3, and we gave it to them. They can't be upset. They can only give us 100% for our beautiful work. Okay, good. Other idea for parametric that you need to know is arc length. So I know in part 2, I'm pretty sure we went over arc length formula for Cartesian rectangular coordinates. You don't have to convert to rectangular to do arc length problems. You can stay in parametric land. It's very lovely. So arc length is going to be integral from a to b square root dx dt squared plus dy dt squared dt. And this formula you'll see again, if you take Calc 3, you'll just add dz dt squared. Boom. Okay, so here we go. They gave me x and y and the limits for t. These are super straightforward. You don't even have to graph them, which is nice. Why do students hate graphing? Let me know down below. I don't know what it is. Okay, is it just that you're bad at it and it's hard? Or is it genuinely not fun? Okay, derivative of 6 sine t, that's going to be 6 cosine t minus, and then look, we got to do product rule because we have 6t times cosine t. So derivative of 6t is 6, leave cosine t alone, plus leave 6t alone, derivative of cosine t is negative sine t. Yeah? Okay, so we have 6 cosine t minus 6 cosine t plus 6t sine t. So this is just 6t sine t. Yes? Bam. Bam. Okay. Now let's get dy dt. So derivative of this guy right here, derivative of 6 cosine t is negative 6 sine t plus, and then again, look at this product rule, 6t and then sine t, so product rule time. So derivative of 6t is 6, leave the other guy alone. They just take turns, that's what I think. 6t times cosine t. And then whoever sat there and wrote this problem really loves us. Look at how things just clean up beautifully. Okay, so 6t cosine t. Now, I like to clean up this whole expression, dx dt squared plus dy dt squared, as much as possible before I write my whole integral out, just so that, you know, I'm not rewriting the integral and all the details just because I'm doing some algebra. So, dx dt squared plus dy dt squared, let's see. If I square this guy, you got to square the whole thing. So it's going to be 36t squared sine squared t plus, and then square this whole guy, 36t squared cos squared t, like that. And then, oh, look how fabulous. I can factor out 36t squared. And then I'm just left with sine squared t plus cosine squared t. This is 1, so this is just 36t squared. I love it. We can take the square root of that and integrate, no problem, right? Okay, so the arc length is going to be integral from 0 to pi over 4 of the square root of just 36t squared dt. Now, technically, square root of 36t squared is absolute value of 6t, right? But I don't need to worry about keeping the absolute value because I'm integrating from 0 to pi over 4. Those are limits for t, and it's positive. So I don't have to keep absolute value. It's already positive. We are good to go. But just think about it, okay? Antiderivative of 6t is 3t squared, and we're going to evaluate from 0 to pi over 4. So that's 3 times pi over 4 squared minus 0. So 3 pi squared over 16. Okay, good. Did you like that problem? I love parametric arc length problems. They're so lovely. Okay. I got one more for you, surface area. And surface area formula is very similar to when you're doing it in rectangular coordinates, okay? So S is equal to 2 pi integral. If you're spinning around the x-axis, it's y. And then you add the little arc length portion, right? So you can call it ds, or you can call it dx dt squared plus dy dt squared dt. Later, you probably should have seen it now, but you'll see it more in Calc 3. This is called ds, okay? So you have the y here if you spin around the x-axis. And then if you're spinning around the y-axis, then you would have 2 pi integral x. And I'm just going to write ds because I'm tired, you know. But I'll tell you, this is if you spin around y-axis. And you're not going to actually leave x or y in the integral. You're going to replace them with the appropriate parametric equation because this is an integral in terms of t. So everything needs to be t's, okay? So we're spinning around the x-axis for this problem. So I know surface area is going to be 2 pi. The limits they gave me right here, 0 to 2 pi. Cool. 0 to 2 pi. Y. Y is 2 plus cosine t. And then I need to figure out all of that stuff. Okay, so let's do it. So what's dx dt? Dx dt is just cosine t. What's dy dt? Derivative of 2 is 0. Derivative of cosine t is negative sine t. Okay, so dx dt squared plus dy dt squared. That's cosine squared t plus sine squared t. Someone must really love us. What a nice and easy problem they wrote us. Okay, so surface area is going to be 2 pi integral 0 to 2 pi 2 plus cosine t square root of 1 dt. Nice, huh? Oh my god. Okay, so leave this 2 pi out. Antiderivative of 2, 2t. Antiderivative of cosine t, sine t, very good. And then we're evaluating from 0 to 2 pi. Leave the 2 pi out, okay? Let's see. Plugging in 2 pi, you have 4 pi plus sine of 2 pi is 0 minus 0 plus 0. So we just have 2 pi times 4 pi. That's 8 pi squared. Okay, good. So you need the arc length formula whenever you do surface area problems, right? It's just like in rectangular. Very nice. Now we're going to talk about polar coordinates. So if you remember this diagram, then you'll be able to go back and forth from polar to rectangular very easily. Just look at your normal trig functions, ratios with a right triangle. So this point is r theta, but it's also x comma y. So this side of the triangle is x, the adjacent side with respect to the theta that's drawn there, and this y here is the opposite side. So you can see cosine theta is adjacent over hypotenuse, x over r, which is where we get x equals r cosine theta, one of the equations that we use when we're converting back and forth. And then similarly, sine of theta is y over r, so y equals r sine theta. Also, this is a right triangle, yeah? So x squared plus y squared equals r squared. And if you're trying to find theta, tangent of theta is y over x. I don't write that theta equals tan inverse of y over x because we have a restriction, yes, on tan inverse, and we don't want to use it because we could have angles in other quadrants. So just write tangent of theta is y over x, and then you'll have to figure out, depending on the quadrant, what theta is. Okay, so just warm up problems before we get into the calculus. Replace the polar equation with an equivalent Cartesian equation. So they want you to switch everything to x's and y's. So to do that, if you see an r cosine theta roaming around in the equation, replace it with an x. If you see r sine theta roaming around in the equation, replace it with y. At the moment, I see none of that. I'm looking here and I'm like, oh man, I wish you had an r. I wish you had an r. There's an r sitting over there. Can I make my dreams come true? Yeah, I'm gonna multiply everything by the denominator. Okay, just move it over. And then it's gonna distribute, right, to the r on the other side. So then you've got r times 5 cosine theta minus r times 3 sine theta equals 1. And then you can say, oh my goodness, that's x. So we have 5x minus 3y equals 1. And you're done. That's just a line. It's in standard form. If you want to put it in y equals mx plus b, knock yourself out. You don't need to do anything though, okay? All right, let's try, oh, I did have another one. R squared sine 2 theta 32. Again, what is this 2 theta doing here? So let's replace it, sine 2 theta with the double angle identity. So we have r squared times, do you remember it? 2 sine theta cosine theta equals 32. And then you can break it up, put the 2 outside. R squared means you have 2 of them, doesn't it? So give 1 to the sine theta, give 1 to the cosine theta. Now everyone's happy. 2y x equals 32. I would divide by 2 and just say xy equals 16. Boom. Okay, good. That's enough of a warm-up. Let's get this show on the road. So find the slope of the polar curve at the indicated point. They gave us that r equals 6 times 1 plus cosine theta, and that theta equals pi over 4. So the formula for slope in polar is pretty much the same as it is in parametric. So dy dx is going to be y d theta over dx d theta. But you're like, they didn't give me x and y, they just gave me r. I know, you got to go figure it out yourself. So y is r sine theta, which means y would be 6 times 1 plus cosine theta times sine theta, like that. You got to make it yourself. And then x is r cosine theta, so x would be 6 times 1 plus cosine theta cosine theta. You see? So you make the parametric equations yourself from the polar equation. It's fine. It's fine. Now let's take derivatives. dy d theta. I'm going to need product rule, right? Because this is one function and then this is one function. And the 6, I'm just going to leave it outside. Okay. So we're going to have 6 times derivative of 1 plus cosine theta is negative sine theta. Leave the other one alone. Plus, now I leave 1 plus cosine theta alone. And then derivative of sine theta is cosine theta. Yeah. Okay, let's clean this up. So this is negative 6 sine squared theta. Plus, I'm going to double distribute, try to keep up. 6 cosine theta plus 6 cos squared theta. I'm not going to need to take the derivative of this again. And they're actually wanting me to plug in pi over 4 for theta. Let me just do that now. Sometimes it makes life nice. So let me evaluate this at theta equals pi over 4 right now. So sine at pi over 4, I know a lot of you guys know it as rad 2 over 2, but it's also useful to think backwards before you rationalize the denominator, and it was just 1 over rad 2. And so if I square 1 over rad 2, it just becomes a half, see? And then 6 cosine theta, so that's 6 times, I'm going to do rad 2 over 2, so it's already rationalized. And then 6 cos squared pi over 4, again, 6 times a half. You see that? Oh, and then this is negative 3, this is positive 3, that cancels. And I'm just left with 3 rad 2. That's dy d theta. So that means that's going to be in the numerator like that. So I already know it's going to be 3 rad 2 over something. So now let's find dx d theta, and I'll plug in pi over 4. You can plug it in at the very, very end. It's up to you. I'm feeling impatient. I wanted to plug it in right now. Dx d theta. Again, I'm going to leave the 6 out, and then we have to do product rule. We have 1 plus cosine theta and then cosine theta. So 6 stay outside. Derivative of 1 plus cosine theta, that's negative sine theta. Leave the other guy alone. Plus, and then leave 1 plus cosine theta alone. Derivative of cosine theta is negative sine theta. Okay. So what happens now? Negative 6 sine theta cosine theta. Let's distribute. Minus 6 sine theta minus 6 sine theta cosine theta. Right? Yes, right. Okay. Nothing cancels this time. It's negative 12 sine theta cosine theta minus 6 sine theta. Okay. So dx d theta, let's evaluate it at theta equals pi over 4. That's negative 12 times, see again, I'm going to think of them as 1 over rad 2 because it's going to be easier to clean up. And then when I have just 1 by itself, I go back to rad 2 over 2. Because rad 2 times rad 2, that's 2. Negative 12 times a half, that's negative 6. Minus, this is 3 rad 2. So that is dx d theta. So I can get rid of the question mark. And then I have -6 minus 3 rad 2. Well, that is not simplified. No, 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 no. So let's clean it up. I'll do it down here. So dy dx at the moment is 3 rad 2 over, let's take the negative out, 6 plus 3 rad 2 like that. And I can divide everybody by 3, and I'll put the negative just here. So I have rad 2 over 2 plus rad 2, right? After I divide everybody by 3. Okay, this is still not simplified because you need to rationalize the denominator. So I have to multiply by the conjugate in order to do that. Yay, algebra. So this is negative. This will distribute, yes? 2 rad 2 minus 2 over, this is 4 minus 2, so 2. And then this cancels. This is a 1. So I've got negative rad 2 minus 1, which is 1 minus rad 2. Wow. That cleaned up so much. Okay, if you didn't make any mistakes and you can do this all on your own, good job. Good job. Okay, so that's that for derivatives. Now let's talk about area. So area in polar is 1/2 integral alpha to beta. Those are limits on theta, r squared d theta. Okay, so this problem here says find the area inside one leaf of the 4-leaved rows r equals 3 sine 2 theta. And I put like a little polar graph there because you know what? Even though the problem doesn't say graph, in order to figure out the limits of integration, you should graph, okay? And this is going to be a repeated theme, especially when you get to Calc 3, if you get there. There's all sorts of problems, and they won't tell you graph, but you can't even set them up without a graph, okay? You just got to be a little graphing machine. So these 4-leaved rows can be a little tricky. It's going to have like this, you know, 4 little petals. You just want inside one of those petals. So I want to know how long it takes for theta to come back and close a loop of the petal. So what I do is I just take the equation 3 sine 2 theta and I set it equal to 0. So basically I want to know when is sine 2 theta equal to 0. So that means 2 theta, let's think. Sine is 0 at 0, and then every multiple of pi after that, plus or minus that. So at 0 plus pi k, where k is an integer, yes? So that means theta, if I divide everything by 2, is going to be, well, 0 divided by 2 is 0. We don't even need it in there. Pi over 2k. So every pi over 2, a loop of this rows is completed. And you can make a nice little table if you want to kind of see it. R equals 3 sine 2 theta. And we'll just go from, let's do 0, pi over 6, pi over 4, pi over 3, and then pi over 2. And that'll be a loop, you know. So at 0, it's 0. If I plug in pi over 6 for theta, it's 2 times pi over 6. So that's going to be pi over 3. Sine of pi over 3 is rad 3 over 2. So this is 3 times rad 3 over 2. Rad 3 is about 1.7. Half of it is going to be like 0.85. And then times 3, just think it's 1.5, you know what I mean? So then you'll have 1.7 plus another 0.85. That's how I would think about it. Why am I doing all this? Because I don't give my class a calculator, so they have to kind of just eyeball it. So it's about 2.55. Okay, at pi over 4, that's 2 times pi over 4. So that's pi over 2. Sine of pi over 2 is 1. So 3 times 1, that's 3. That's going to be like the furthest tip of the petal, right? That's going to be the longest part. And then when we go back to pi over 3, sine of 2 pi over 3, also rad 3 over 2 times 3. So again, 2.55, and then we're back to 0. This is with no calculator. So obviously, like here, if I were to do it, 3 sine 60, yeah, it's not 2.55. It's really like 2.6 if you put it in the calculator. But I'm doing my crude approximation that my students do because I don't allow a calculator. Okay. So here we go. Here's the polar. This is pi over 6. This is pi over 4. This is pi over 3, pi over 2. We're going to get one loop. So 0. Pi over 6 is 2.5-ish. Pi over 4, it hits 3, and then it comes back. So it like closes the loop here. And then if you wanted to draw more, I don't, but they would be here, you know. Every pi over 2, another one gets traced out. Here, I'm just gonna draw it in. 1, 2, 3 here. Okay, so since they only want one petal, I can see the limits should be from 0 to pi over 2, however long it takes to draw out one petal, right? It goes from 0 all the way back to 0. There we go. If they wanted the area of the whole thing, don't integrate 0 to 2 pi, just do one petal and then times 4, right? Okay. So here we go. The area is going to be, take the 1/2 out, limits are 0 to pi over 2, and then you have r squared, so 3 sine 2 theta squared d theta, like that. Okay, let's clean it up. So this squared will distribute. So that's going to be 9. That 9 goes outside. Take the constants out. It will make life so nice. Sine squared 2 theta d theta. To integrate sine squared or cosine squared, we always use our half angle identity. So this is 9/2 integral 0 to pi over 2. I'm going to replace it with 1/2, 1 minus cosine, and then you always double whatever angle is there. So in this case, it's going to become 4 theta d theta. Good. Again, this 1/2, bring it out with the 9/2. So this is 9 over 4 integral 0 to pi over 2. I guess I could have integrated already. So let's do it in the next step. So this is 9/4. Antiderivative of 1 is theta. Antiderivative of minus cosine 4 theta minus 1/4 sine 4 theta from 0 to pi over 2. So this is 9/4 times pi over 2 minus 1/4 times, that's going to be sine of 2 pi, so that's 0 minus 0 plus 0. 9/4 times pi over 2. Why, that's 9 pi over 8. Okay, good. I think the hardest part is figuring out the limits of integration. The actual integrals are not too challenging. So graph, people, just graph. Okay, here's a spicy one. I told my students it's on the final. I know, who am I spilling the secrets already? You want to know why? Because it's hard. And I want them to know how to do it. So I feel like if I at least tell them, the ones who care will study it. So here we go. This is, again, find the area inside the circle, rad 3 sine theta, and then outside the cardioid, r equals 1 plus cosine theta. So here's the thing. The more you learn the polar equations, you'll know what the graphs are very easily. If I just look at this, I know this is a circle centered on the y-axis, and the radius is rad 3 over 2. So whatever number you see in front is the diameter. And then we have this cardioid 1 plus cosine theta. Because it has cosine in it, then I know it's centered on the x-axis. Okay? So first things first, you have to find where they intersect. I need to find the intersection. so I can determine the limits of integration and draw an appropriate graph. Did it say graph anywhere? No, but you better graph it. Oh my God, how do you solve this equation? So I always, most of them are easier than this. You can set things equal to 0 and factor, or, you might have to use some quadratic properties. When nothing is squared and it's not going to be factorable, you square both sides. Yes, you do. Like this. Okay. So the left-hand side is going to become 3 sine squared theta. And then the right will be 1 plus 2 cosine theta plus cosine squared theta. And then now I have to decide, okay, is this equation going to end up in terms of only cosines or in terms of only sines? Usually you don't want to mix. Well, I'm stuck with this guy, right? Because it's not squared. So it looks like everything has to be in terms of cosines. So I'm going to replace sine squared theta on the left now with 1 minus cos squared theta. And there's the 3. Okay. Now I know I have a quadratic equation, right? So 3 minus 3 cosine squared theta equals 1 plus 2 cosine theta plus cos squared theta. Let's just move everything to the right so it's all positive. Let's keep a positive disposition going. So we have 4 cosine squared theta plus 2 cosine theta minus 2. Before I factor, let's just divide everybody by 2. So 0 equals 2 cosine squared theta plus cosine theta minus 1. Can you factor? You should be able to. 1, 1. This should be plus. This should be minus. Okay, so this means cosine theta is 1/2 or cosine theta equals -1. So let's see, cosine theta is 1/2 at pi over 3. Also, cosine theta is 1/2 in quadrant 4 at 5 pi over 3. Cosine is -1 when theta is pi. Now, one thing you do need to be careful about when you square both sides of an equation, sometimes you pick up extraneous solutions here that don't work in the original. So the original, before we tampered with things and squared both sides, was this guy, right? And you should check that all of them still work in there. We might have something extra that we have to throw away. So I'm just going to mentally check. So pi over 3. Sine at pi over 3 is rad 3 over 2. Rad 3 over 2 times rad 3, that's 3/2. Equals 1 plus 1/2, that's also 3/2. Okay, so that one checks. 5 pi over 3. Sine of 5 pi over 3 is negative. So then this would be -3/2. Okay, so that one doesn't work. Check that one out. Pi, sine of pi, that's 0. So this is 0. And then cosine of pi is -1, so that checks out. Okay, so these are the only 2 true points of intersection for the curves. Pi over 3 and pi. Okay. So let's see if we can draw them now. Rad 3 is the diameter. And just to make it nice, I'm going to call this rad 3. So that's like about 1.7, right? And then this is rad 3 over 2. You can scale your graph how you want. It is your world, okay? Live your life. Boom. So that's the circle. Now the cardioid, r equals 1 plus cosine theta. I feel comfortable just to sketch it. If you don't, then go ahead, let's make a table, okay? Theta and then r. We already know the points of intersection, right? It's pi over 3 and pi. At pi, they're all just 0. At pi over 3, well, I'm good. 0, this is going to be 1 plus 1, so 2. So we've got 0, 2. Because of how I scaled it, it's going to be like, that's 1.7, 0.85. It'll be kind of more like here-ish. Then let's plug in pi over 3. So that's going to be 1 plus 1/2 So 3/2, 1.5-ish. Yeah, I'll buy that, because if I'm calling this 1.7, yeah, that looks like 1.5. Go us. And then you can just reflect that on the other side if you want. Or we can do pi over 2 is just 1 plus 0. So 1, I'll just pretend that's point, like say 1 is here. Okay, 1, 2, and a wee bit more. 1, 2. So I'm just reflecting now. Okay. We'll just have something like this. And then mirror it on the other side best you can. 1, 2, 3, and a wee bit more. 1, 2, 3, and a wee bit more. Like that. Okay. It's not perfect, but it's enough for us to get an idea. There's the cardioid. There's the circle. And then let's see if we can identify the region that we have to find the area of. Inside the circle, outside the cardioid. Inside the circle, outside the cardioid. It's this right here, right? Okay, so when you have an area bounded by two regions, the formula is as follows. So you're going to have area equals, you still do the 1/2 alpha to beta, and then you have outer radius squared minus inner radius squared d theta. Okay, so how do you figure out which one's the outer radius, which one's the inner radius, and alpha and beta? I will show you. And this is a trick you're going to use in Calc 3 also. So when you're figuring out your limits for theta, start at 0, sweep out, imagine counterclockwise, and see where the region starts and where it stops in terms of theta. So no area, no area, no area. I'm looking in reference to here, right? No area, no area, no area. Here's some area. Where is that? That's at theta equals pi over 3. Okay, we've got area, 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 area. Oh, it's done. It is done. Where is that? That is at theta equals pi. Okay, so those are my limits of integration. Pi over 3 to pi. Pi over 3 to pi. Okay, cool. What's the outer radius? What's the inner radius? From the origin, draw a ray. Wherever you want. Through the region, okay? Wherever it hits first, that's the inner radius. Wherever it hits second, that's the outer radius. Outer radius is the circle. Inner radius is the cardioid. Okay, can you see? Draw yourself a ray going from the origin through the region. It hits first, that's the inner radius. It hits second, that's the outer radius. Okay, so that means we're going to have rad 3 sine theta squared minus 1 plus cosine theta squared d theta. When you are in polar, you're no longer thinking top minus bottom, right minus left. You're thinking in terms of circles, okay? Outside, inside, and then sweeping theta. You got to get that Cartesian training out of your brain. Just think in terms of polar now. Okay, and then we got to integrate this. So we've got 1/2 pi over 3 to pi. Now would be a good time, pause the video, see if you can do it without screwing it up on your own, you know? How dare I say that? No, I said it. Okay, 1 minus 2 cosine theta minus cosine squared theta d theta. Okay, I have a cosine squared and a sine squared, so we're going to use our half angle identities. So pi over 3 to pi, 3 times 1/2. You know what? Let's just write 3/2. 1 minus cosine 2 theta minus 1 minus 2 cosine theta minus 1/2 times 1 plus cosine 2 theta. We can clean up more, right? Because this is 3/2 minus 3/2 cosine 2 theta. And then this is minus 1/2 minus 1/2 cosine 2 theta. So we can combine like terms. I have 3/2 minus 1/2, that's 1. Positive 1. Minus 1, that all cancels. Oh, great. Love it. What else? Anything else good happening here? Minus 3 halves, minus a half, that's minus 4 halves, so minus 2. Okay, I'll take it. So 1/2 pi over 3 to pi minus 2 cosine 2 theta. And then u, the little loner, minus 2 cosine theta d theta. Let us take the 2's out of the integral if we want, because it'll cancel with the half. Yeah? Okay, so I'm going to have 1 negative 1/2 times 2, and then we're going to go pi over 3 to pi, and then this is cosine 2 theta plus cosine theta d theta. And then, I'm just going to, this is 1. I want to get rid of the negative. I'm going to flip the limits of integration. I know. I like to get it as clean as possible before I integrate. It saves you from making mistakes. Okay, antiderivative of cosine 2 theta. That's 1/2 sine 2 theta. 2 theta. Plus antiderivative of cosine theta is sine theta. And now we're going from pi to pi over 3 because I wanted to get rid of the negative. Okay, so this is 1/2 times sine of 2 pi over 3. Sine of 2 pi over 3 is rad 3 over 2. Plus sine of pi over 3 is also the same. Minus 1/2 times sine of 2 pi is 0. Plus sine of pi, also 0. So what is this? Rad 3 over 4 plus rad 3 over 2, which is 2 rad 3 over 4. So this is 3 rad 3 over 4. Wow, what a spicy little problem, huh? Okay. Anyways, I'm not saying every semester I'm going to put this on the final, but I warned them this semester. They're going to see it on Monday. Okay, now, moving on. I think this is the last thing I'm doing in this video. Find the length of the curve. So arc length formula for polar, we have its own proper formula. Like you don't need to change it to parametric and use the parametric formula. I mean, you can, but it's just more work, worthless, and you're going to do the same Pythagorean identity. So arc length formula when you are in polar goes from alpha to beta, and then you have square root of r squared plus dr d theta squared d theta. Okay, so let's go ahead and take the derivative of r. I think it's helpful, especially if you struggle with the chain rule and stuff, to just move that cubed all the way on the outside so it's a little easier to differentiate properly. So dr d theta, remember you bring the exponent down in the front, so that's going to be a 9. I always write the new exponent right away so I don't forget. And then you have, leave this alone. Then by the chain rule, I have to multiply by derivative of the next layer. So what's the derivative of sine something? It's cosine something. And then now next layer, what's the derivative of theta over 3? Just think it's 1/3 times theta. So then it's just going to be 1/3. And then the 9 and the 1/3 cancel. This is just a cute little 3. So this is 3 sine squared theta over 3 cosine theta over 3. So now let me see. I like to clean all of this up as much as possible before I set up the whole integral. So let's see. R squared is just the OG function squared. So r squared plus dr d theta squared is going to be 9. That'll be sine to the 6th now, right, of theta over 3. Plus, I have to square all of this. So it'll be 9. Now sine to the 4th of theta over 3. And then cosine squared theta over 3. There's got to be some cool factoring that's going to make life better. This is too nasty to integrate. So I can take out a 9 and sine to the 4th of theta over 3 from both terms. And then I'm just going to have sine squared theta over 3 plus cosine squared. Oh, theta over 3. Beautiful. That's 1. I can take the square root of this guy in my sleep. Yes. Okay, so arc length is going to be integral. Alpha to beta is going to be 0 to 1/2. They gave me the limits on theta already. 0 to pi over 2. Why am I saying 1/2? And then square root 9 sine to the 4th theta over 3 d theta. Okay, so square root is going to be 3. Let me take it out. 0 to pi over 2, and then that's sine squared theta over 3 d theta. Same old, replace it with the half angle. You're going to have a 1/2. I'm taking it outside. 0 to pi over 2, 1 minus cosine. Be careful, it's 2 theta over 3 now. Yeah, you always double the angle. And then we're going to integrate. Okay. So antiderivative of 1 is theta. Antiderivative of negative cosine, think of it as 2/3 theta. It'll be minus 3/2 sine 2 theta over 3 from 0 to pi over 2. Okay, 3/2 times, this is pi over 2 minus 3/2 times, that's going to be sine of pi over 3, rad 3 over 2, minus 0 plus sine of 0 is 0. So what is this? 3 pi over 4 minus 9 rad 3 over 8. And I would just leave it like that. Yeah, you can get a common denominator if you want. You can make it 6 pi minus 9 rad 3 all over 8, whatever. I don't know. Check with your teacher how much they care. Do they care? Last topic, briefly, conic sections. So it's asking us to find the vertex, focus, and directrix of the parabola. So when we're talking about conic sections and parabolas, we can have them opening up and down or right and left. They don't need to be functions of x. So just remember there's 2 forms. You could have x minus h squared equals 4p times y minus k. That's for one that's opening up or down. Or you would have y minus k squared equals 4p times x minus h. That would be one opening this way or that way. Okay. If you forgot what p is, that's the distance from vertex to focus. And then hk is the vertex. Okay. We have to complete the square in order to figure out where everything is. So I'm going to add 36 here, and then I have to add 36 on the other side. Why 36? Divide this by 2 and square it. So then we'll have x minus 6 squared equals 8y minus 40. So that's x minus 6 squared equals 8 times y minus 5. So this number right here is 4p, so 4p equals 8, so p equals 2. Since x is squared, that means this guy's opening up or down, but I know it's up because this is positive, okay? And then the vertex is at 6, 5. So start graphing, and then I answer all the rest of the questions. So 6, 5, here's the vertex. And then the distance from the vertex to the focus is 2, because p was 2. And I know the parabola is opening upwards. The focus is always sitting inside like that. The parabola looks like it wants to eat the focus. Like you're playing Pac-Man and it's a little circle it wants to eat. Gobble, gobble, gobble. Okay, so you're going to go up 2 from there. So right here is the focus, and that's the vertex. So just think, from the vertex you went up 2. That means the focus is at 6, 7. Okay, then it wanted the directrix. The directrix is the same distance, p, that the focus is from the vertex, but the other way. So it's going to go down 2 units, and it's going to be a horizontal line. The parabola doesn't touch it. So what's the equation of that line? Directrix is at y equals 3. Now, how fat or skinny is this parabola? Well, you use the focal width, which is 8, to help you out. At the focus, the width is 8. That's why this is called the focal width. It's 8 across. That means from here, it'll be 4 this away, 4 that away, 4 to the left, 4 to the right. And where are we? We're at 6. So go to 2 and then go to 10. And that's how fat it is. And you just go like this. No, I didn't find the y-intercept. They didn't ask me to, so I'm not doing it. Okay, just cross it wherever your heart desires, unless your teacher's a stickler. So that's it. We graphed it. We found what they wanted. We're moving on with our lives. Find an equation for the parabola described. Vertex is at 6,2, focus is at 6,4. So I know HK. And from here, I just start graphing. Did they tell me to graph? No. But you know what? It just helps you orient everything. Because at the moment, do we know if it's an x squared or a y squared parabola? If I graph it, I can tell really easily. So 6,2 is the vertex, and then here's the focus. And I just told you it always looks like it's going to eat the focus, so it's opening this way. So if it's opening upwards, it's an x squared parabola. So I know I have x minus h squared equals 4p times y minus k, like that. Okay, we know h and k. And actually, you can tell what P is if you just look at how far apart the vertex and the focus are. Oh my God, I need to get some new numbers. Why is it all turning out the same, huh? Okay, so it is at 4, comma, oh, I was trying to figure out where it was. Here, P is 2, right? These are 2 apart. So P equals 2. And then we have h and k, so it's going to be x minus 6 squared equals 8 times y minus 2. And that's it. Do we want to do one that opens the other way? I feel like we should. Okay, let me add a quick little example just for variety's sake, because that one was too similar to the one right before. Okay, vertex at 1, -2. Focus at 8, -2. Okay, again, they didn't say to graph, but we will. Vertex is at 1, -2. There's the vertex. And then the focus is at 8, -2. There's the focus. And remember, the parabola always looks like it's going to eat the focus. So it has to open up this way. So that means it's a y squared parabola. See how graphing really helps? So then I'm going to have y minus k squared equals 4p times x minus h. This distance here is p. So you can just count. It went from 1 to 8, so p is 7. And then here's my h and k. So y plus 2 squared equals 4 times 7. That's 28 times x minus 1. And you're done. I think these problems are so fun because it can show if you know what's going on, but it doesn't take like a lot of tedious work, you know? Okay, good. I feel better. I did that one for you guys. I didn't want you to be like incomplete. Now, moving on to another conic section. One of my favorites, the ellipse. So we need to find the center, foci, and vertices of the ellipse. So we need to complete the square to get it in standard form. And everything needs to equal 1. So I'm going to group all the terms with x together. 2 times x squared minus 12x plus, we'll see, plus, and then y squareds together. I'm going to also factor out the coefficient on the squared term. 5 times y squared plus 70 divided by 5 is 14. Plus something equals -307. So let's see, to complete the square, divide this constant by 2 and then square it. So I'm going to add 36 over here. Really, I added 2 times 36, so I'm going to add 72 over here. And then same thing for y. 14 divided by 2 is 7. Squared is 49. And then 5 times 49 is 245. So then now I can rewrite left-hand side in factored form. So it's 2 times x minus 6 squared plus 5 times y plus 7 squared. All of this equals 10. If you're bad at completing the square and you just need a refresher, then go back to the full-length lecture videos because I go through super slowly as if you're learning it for the first time. But I'm assuming you guys are in Calc 2, so you should have seen this in pre-calc already. Okay, and then for an ellipse, you always need a 1 on the right-hand side. So whatever constant you have, divide it by itself so that you do have a 1. And then we have x minus 6 squared over 5 plus y plus 7 squared over 2 equals 1. Now in the denominators are a squared and b squared. How do you know which is which? A is the bigger one. So this is a squared and this is b squared. And I can already see where the center is, right? The center is at 6, -7. To get the foci, I need to find what c is. And for an ellipse, a squared minus b squared equals c squared. You just got to memorize that. So 5 minus 2 is c squared. So c is rad 3. Since a is underneath x, that means the major axis is parallel to the x-axis. So the vertices are going to be in the x direction, and the foci I'm going to add and subtract from the x coordinate of the center. So the foci are at 6 plus or minus rad 3, -7. And then the vertices, there's only 2. The vertices are going to be, again, added and subtracted from the x coordinate since a is under x. A is rad 5. So the vertices are at 6 plus or minus rad 5, -7. Okay? If the 2 was here and the 5 was here, then I would be doing everything to the y coordinate. Do we have to do anything else? No. We could graph, but I don't want to, and they didn't ask me to, so I'm not going to. If you need to draw it to help you figure out where the foci are, where the vertices are, then do it. Okay. Let's see, what else did I pick out for you guys? Find an equation for the ellipse described. Graph the equation. I like this one. So foci are at -1, 5 and -5, 5. These are the foci. And then one of the vertices, that's why they say vertex, is at -6, 5. Okay. I can see the foci are moving in the x direction, right? So that means a is under x. If the foci were like this, then a would be underneath y. So I'm already going to write out x minus h squared over a squared plus y minus k squared over b squared is 1. I need to know where the center is to figure out a, b, and c. So the center, since they gave me the 2 foci, it has to be halfway between, right? This is at -5, this is at -1. They're 4 apart. Half of that would be 2 units from each one. So the center is at -3, 5. Right? -3, 5. There's the center. C is the distance from the center to one of the foci. So C equals 2. And then the distance from the center to one of the vertices is A. So A is 3. Okay, so center to one of the foci is C. Center to one of the vertices is A. So I got H and K. I have A. I don't have B. So to get B, you're going to use A squared minus B squared is C squared. A squared would be 9 minus B squared equals 4. So B squared is 5. Oh, that's actually enough. I can write the equation now. So we have x plus 3 squared over 9 plus y minus 5 squared over 5 equals 1. Oh, they did want me to graph, didn't they? They sure did. Okay, so A is 3. What was B? B is rad 5. Oh, not a nice number. A wee bit more than 2, but not 3. So that means from the center, go up and down just a wee bit more than 2. Let me erase all this so it's not so messy. From the center, 1, 2, and a wee bit more. Those are just the foci. And then A is 3. So one of the other vertex that they didn't give me is right there at 0, 5. So here, it's my ugly little ellipse. Okay, so this is one of the vertices that they gave me, negative 6, 5. Here's the center at negative 3, 5. Other vertex would be at 0, 5 because 3, 3, yeah? And then these are the foci, I just left them in. And then these are the endpoints of the minor axis. So you go center, this distance here is B, rad 5, up and down. They're not called vertices. Poor things. Only the endpoints of the major axis are called vertices. Okay, who's left? The hyperbola. How do you know you have a hyperbola? Because there's a minus sign either in front of x squared or y squared. Okay, they've almost got it in standard form for us, but not quite. Remember, we need a 1 over here. I don't know why they just like gave up partway through, but okay. Y plus 4 squared over 9 minus x minus 2 squared. I'm going to put over 1 equals 1. Now just be careful because they put y first. So when you're writing out the coordinates of the center, pay attention. It's going to be 2 comma negative 4, right? Not the other way around. A squared is always underneath the positive variable. It's not necessarily a bigger number than b. In this case, it is though. So since this is the positive term, yes, okay, that's a squared. And then that's b squared. Okay, so a is 3 and b is 1. And I have the center. Why is that helpful? So I'm going to go negative 2, 4. There's the center. You go 3 up and down from the center because that's underneath y. So up 1, 2, 3, down 1, 2, 3. Those are my vertices. And then 1 to the left, 1 to the right. Then you make your fundamental rectangle. Then you make the asymptotes through the diagonals. And in this case, since the y coordinate, the y squared term is positive, this hyperbola opens up and down, up and down, like that. They didn't ask us to find vertices and foci, but let's just do it. So this is one of the vertices, that's another one. They're from the center plus or minus 3 in the y direction. So they would be at 2, negative 1, and 2, negative 7. If you want the foci, well, for a hyperbola, we use a squared plus b squared equals c squared. So that means 9 plus 1 is c squared. C is rad 10. And that rad 10 gets added and subtracted to y coordinate of the center. So foci are at 2 comma negative 4 plus or minus rad 10, which is like a wee bit more than 3. So it'll be like here and here. And again, it always looks like, you know, the hyperbola is eating the foci. It should sit inside just like it does on the parabola. Let's get the equations of the asymptotes. Why not? So the slope, I just count from the center to the corner of the fundamental rectangle. Just do rise over run. So it's going to be 3 over 1. And then the other asymptote, this one, just has the negative slope, same number, up 3, 1 to the left. So the slope for the asymptotes is plus or minus 3. And they both go through the center, HK. So I just write it in point slope form, like y minus y1 equals m times x minus x1, and use h and k. because that's where both asymptotes go through. So you can just combo them into one equation and just write y plus 4 equals plus or minus 3 times x minus 2. I'm fine with my students if they leave it like this. I don't need them to like separate the two and rewrite it in y equals mx plus b. Who cares? But if your teacher wants it, you got to do it. Make them happy. It's all about making your teacher give you full credit. So if you know they want it a certain way, do it. Okay. That's the hyperbola. That was really quick review. But like I said, conics you should have seen before. If you need a lot of detail, I can link all the videos in the description. I just don't want this to be a 5-hour review video. And okay, that concludes part 3. Part 4 will be sequences and series, but it probably won't come out anytime soon. I know. I'm tired. I'm busy. And also, I told my class, since they just took a test on sequences and series, there wasn't going to be a ton of it on their final. So they're fine. Maybe you need a big review. So just check out my playlist for Calc 2. All of the video lectures are there. You can watch them on double speed if you need it quick. If you made it to the end, let me know. Oh my goodness. I need to get ready, go to ballet later today. Hope everyone has a fabulous weekend. Whenever you're watching this, it might be a year or 2 from now. I hope things are going well for you. Anyways, give the video a thumbs up. Leave me a comment if you made it this far. I'm curious. And subscribe if you haven't already. I'll talk to you guys soon. Bye.